Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the central limit theorem. Before, we talked about the law of large numbers, which establishes that if we have independent random variables with mean mu and variance sigma squared, then the sample mean, which is just the average of n such random variables, is going to converge to mu, which is the mean of the distribution, in mean squared and in probability. But we didn't talk about what the distribution of the random mean is. And notice that the random mean is a sum of n random variables, so it is a random variable itself. We studied its mean and its variance, but we didn't talk about its distribution. Here, I'm showing you this example that we had, where we had a population of 4,000 people. We were applying random sampling to try to estimate the mean of the population. Here I'm showing you the histogram of the sample mean when we're averaging over 20 people, and I'm taking 10,000 samples to plot the histogram. What I mean by the distribution is the distribution of these values. We know that they're centered at mu, and we know that the variance scales like the variance of the population divided by n, so that when we consider larger values of n, the distribution concentrates more and more. But what is the actual shape of the distribution? That's what we're going to learn about today. So we want to study the distribution of the sample mean. The prerequisites for this material are expectation and the law of large numbers. In order to study the distribution of the sample mean, we have to learn about what is the distribution of the sum of two independent random variables. So here we're going to consider continuous random variables, but the arguments for discrete random variables are very similar. Okay, so what's the CDF of the sum of two random variables? So let's call Z A plus B. The CDF of C is just the probability that this sum is more than that specific value. What do? Well, we integrate the joint PDF of these two random variables. B goes from minus infinity to infinity, and now to ensure that A plus B is more than C, we integrate A from minus infinity to Z minus B, so that we're sure that A plus B is more than Z. Now here, instead of having the joint PDF, we can write the product of the marginals because these random variables are independent. Now we can actually integrate with respect to A. Because of independence, here we end up with only one term that depends on A, and we can just integrate it. By definition, it's just going to be the CDF at Z minus B. Now, if we are interested in the PDF of the sum of the two random variables, we differentiate the CDF. You might be nervous, and you should be nervous when you have this limit that goes from minus infinity and into infinity. Can I put the differential operator inside? You can, because everything is bounded, so everything is well behaved. We assume that everything is bounded and well behaved. So now we differentiate the CDF and we get the PDF there. This operation is called the convolution, and is usually written like that. It's the convolution between the PDF of A and the PDF of B. And if we had done this for discrete random variables, we would have gotten essentially the same thing, but in discrete. So the discrete convolution, which is a sum, and then this would have been PMFs instead of PDFs. In order to understand a little bit how convolutions work, let's work through an example. So imagine that you have a coffee shop in Manhattan, and you have two suppliers, one from Colombia and one from Vietnam. Your Colombian supplier, the quantity of coffee that they provide over a year can be modeled as a uniform random variable between 0 and 1, whereas your Vietnam supplier provides you with a quantity of coffee that is uniform in 0, 2. And now you're worried about your total amount of coffee. And since maybe Colombia and Vietnam are far enough, we're going to model the crops and so on as if they were independent. So C and V are going to be independent. In that case, the density of the sum is equal to the convolution between the two PDFs. So now this PDF here is non-zero between 0 and 2. So we're just going to integrate between 0 and 2, and it's equal to 1/2 there because it has to integrate to 1. I strongly recommend that you work on this, you try to solve this on your own, and then you take a look at how I do it, because there's no way, there's no way of escaping that. Like, in order to understand how convolutions actually work, you just need to go through the details at least a couple of times. Anyways, so now we have to see where this guy is non-zero. This guy is going to be non-zero if b minus u is between 0 and 1, right? So this means that u is greater than b minus 1 and smaller than b. Okay, so if we put, and at the same time, u has to be between 0 and 2. So when we integrate this thing, this is going to be non-zero between the max of 0 and b minus 1 and the min of b and 2. So now for different values of b, these bounds are going to change. So when we are smaller than 1, maybe I will write this here, so we're a bit like the max. Actually, no, I think we can remember, or we can just go back. So if b is smaller than 1, then the max between 0 and b minus 1 is just going to be 0. So we're going to integrate from 0 to b, because b is going to be smaller than 2, right? So this is integrating from 0 to b, and the answer is b minus 2. Sorry, b over 2. This is, this is as long as b is greater than 0. I should have said this, right? Like here, b is greater than 0. If we're integrating, if b is between 1 and 2, then we're going to go from b minus 1 to b. Okay, so we're integrating from b minus 1 to b, and the answer is 1/2. And if b is between 2 and 3, then we're integrating between b minus 1 and 2, and the answer is 3 minus b over 2. Again, just, I encourage you to compute this on your own. The important thing here is that what we're doing, okay, so these are the two distributions. Essentially what we're doing is we're fixing one of them, and then we're taking the other one and kind of putting it, like sliding it on top. And when we slide, we do, we compute the integral over the product of them. And essentially what we're doing is just a smoothing average of the distribution. So that's why the result looks like that. When they start to overlap, this is where we start to overlap here. Eventually the overlap is complete, so that's why it's constant. Like the integral is constant here. And then they overlap less and less, and eventually it comes to 0. So intuitively, when you convolve a PDF with another PDF, they smooth each other. Okay, the result is always smoother than the individual PDFs. So what happens if you compute the distribution of the sample mean, which at the end of the day is 1 over n x1 plus x2 plus x3 and so on. Every time we sum, again, we're convolving again by the same PDF. What happens? Here I'm going to show you numerically what happens. We start with this PDF, and we're just going to convolve it over and over and over. So the result of convolving it once is this. Now I convolve it again with F1, and again, and again, and again, and again. And what you see is that we converge to something like looks like a Gaussian, which is, at least to me, quite unexpected. And this will happen even if you start with a very weird looking PDF. If you convolve it enough times with itself, eventually it will converge to a Gaussian. And this happens even if you start with a PMF and you just convolve it over and over and over and over and over again with itself. This is the central limit theorem. The central limit theorem states that when you convolve a PDF or a PMF with itself enough times, it will essentially assume a Gaussian-like shape. The formal proof of this is beyond the scope of this video, although maybe in the future I will create a video with a proof. It just gets a little bit complicated mathematically. But it's super important, and it's, you really need to know about it, even if you can't prove it. The idea is that if we have IID random variables with a certain mean and a certain variance, their sample mean is going to converge in distribution to a Gaussian. And what are the parameters of the Gaussian? Well, we already know what the mean of the sample mean is, right? It's just mu, where mu is the mean of the IID random variables. And we know that the variance of the sample mean is the population variance, is sigma squared divided by n. So those are the parameters of the Gaussian. And now we also know the shape of the distribution. Okay, it's going to tend to be Gaussian because of this effect that when you convolve a PDF or a PMF with itself over and over and over, it tends to smooth itself out into a Gaussian. Equivalently, if we subtract the mean and then we divide by the standard deviation of the sample mean, we get something that is a standard Gaussian with zero mean and unit variance. That's the central limit theorem. When we look at the height data, and in particular, we take the distribution of the sample means after we have standardized, which means that we have centered them using the true mean, and we have divided by the standard deviation. Of course, this we wouldn't be able to do in practice, right? I'm just showing you that the statement actually holds. You wouldn't know this, and you wouldn't know this in practice. Okay, it's just to show you that distribution is actually Gaussian. This is the central limit theorem approximation. It looks very, very close to the histogram. For n equals 100, same thing. Of course, the actual distribution would be much narrower, right? Because now we're averaging over 100. So the variance is actually divided by 100, not by 20. But I'm standardizing, okay? I'm normalizing. And this is why this again has variance 1. And then same thing for n equals to 1000. The distribution is indeed extremely close to a Gaussian, as you can see from the histograms fit to the central limit theorem approximation. Okay, so let's see how to exploit the central limit theorem to quantify how many samples we need to take to make a certain error when we're estimating the prevalence of COVID-19 in New York City. We already applied Chebyshev's inequality for this. Now we're going to see that the central limit theorem is much more powerful. Okay, so again, we have a certain population. We want to know what the prevalence of COVID-19 is. We want to make an error of 1% with a probability less than 0.01. We'll state in a moment what we mean exactly by that. And our question is, how large should n be? We already applied Chebyshev's inequality, and we got an answer which was 1 million, which sounds like a lot given the distributions that we have been observing in our numerical simulations. And the reason is that Chebyshev's inequality does not know about the distribution of the sample mean. It just has like this very strict, it's this inequality that has to hold for any possible distribution that has that variance. So in that sense, it's not as powerful as using the whole distribution. Okay, there's the intuition why you might want to use the central limit theorem in this case. Okay, so we have these tests that go from 1 to n. They're independent, they're identically distributed. We know that they're Bernoulli with a parameter that is equal to the prevalence of COVID-19, this proportion that we want to estimate. Because they're Bernoulli, this is their mean, it's equal to the parameter, and their variance is equal to the parameter times 1 minus the parameter. The mean of the sample mean is just equal to the parameter, to the population mean, and the variance of the sample mean is equal to the population variance divided by n. By the central limit theorem, we know that if we subtract the true parameter and then we divide by the standard deviation, then this is going to be approximately a Gaussian with mean 0 and unit standard deviation. Of course, we don't know this, but we'll get to that. So, okay. So what we're going to do is we're going to say, what is the probability that m is greater than the parameter plus 10 to the, 10 to the minus 2, and what is the probability that m is smaller than the parameter minus 10 to the minus 2. by symmetry, we can bound these two probabilities in the same way. So what we're going to ensure is that this probability is smaller than 0.005. Is this okay? So again, like I just want to remind myself. Okay, we want the probability to be smaller than 0.01. So we're going to say the probability that we are too large by more than 0.1 is 0.05, is bounded by 0.005. The probability that we're too small is also bounded by 0.005. Okay? So I'm just explaining why we're focusing on m minus the parameter being above 0.01. We want to bound that probability by 0.05 by the same argument, the probability that that it's smaller than theta than the proportion minus 10 to the minus 2 will also be smaller than 0.05. I feel that I made that unnecessarily complicated, but let's move on. Okay, so now we're interested in bounding this probability. And remember that here the only random thing I do want to remind you is the sample mean, and the randomness comes from the fact that we're selecting people at random. Okay? All right, so we, like basically, what do we do here? We multiply on both sides by square root of n, and we divide by square root of the parameter times 1 minus the parameter. What are we doing? We're dividing by the standard deviation of the sample mean on both sides. And now we know that this is a Gaussian with mean 0 and standard deviation equal to 1. The problem, okay, is that here we have a quantity that we don't know because we don't know the prevalence of COVID-19. This is exactly what we're trying to estimate, so we just don't know it. However, we know that that quantity is definitely going to be smaller than 1 because this parameter theta has to be between 0 and 1. Okay, so we can upper bound this probability by the probability that that random variable is greater than a smaller number. Okay, here we're dividing by something smaller than 1, so the probability that this thing is greater than this has to be smaller than the probability of this being greater than something smaller. I hope that makes sense. Okay, so, and this we need to do because we don't know the parameter. We don't know the parameter. Okay, at least we're assuming that we don't know the parameter. So now, this is just the probability, approximately the probability that a standard Gaussian with mean 0 and standard deviation equal to 1 is greater than this value. We use our computer and we figure out that if we want this thing to be smaller than 0.05, then this thing has to be approximately 2.58. So now we multiply it times 100 and we take, we multiply by 100 and we take the square, and we have that if n is around 67,000, then we're going to make an error of 1%, less than 1% of the time. Okay, that was our goal. Compare this to 1 million, which is what we obtained with Chebyshev's inequality. It's much smaller because we're exploiting the fact that the sample mean has that particular distribution. So it turns out that we probably overestimated this number because of our bound on the variance of the sample mean, right? Like the population variance. So let's just plug in a value and see how good it would have been if we actually knew that, that parameter, just to check how good the central limit theorem approximation is in practice. So if we had put this here, magically, then we would need only the probability, we need to bound only the probability that u is greater than this value, where here we had plugged in 1 because we didn't know that the population, the parameter, the proportion of interest was equal to 0.1. Again, I want to stress that we're only doing this here to sanity check, how good the central limit theorem would actually be if we even knew the standard deviation. So now we plug that in, then we get that we only need 6,000 people. with 6,000 people, we get, we make an error of more than 1% only 1% of the time. So this is pretty impressive, right? You have an 8 million population, you only need to test 6,000 people, and you get a very good estimate of the prevalence of COVID-19 with an accuracy of 1%. And of course, it doesn't depend on the underlying population. Again, intuitively, the idea is that if the prevalence is around 10% and you pick 6,000 people, the fraction of people within those 6,000 people that have COVID-19 is going to be close to 0.1. And the reason why we obtain such a sharp bound is because we're exploiting the actual distribution, not only that it's Gaussian, as in the previous slide, but beyond that, we're exploiting that we actually know the standard deviation, which is something that we don't usually know. Okay, this is just to show you how powerful it can be to actually know the distribution. So as a sanity check, let's see whether how good this value is, because we can actually compute the probability that we make an error of less than 1%. So we make an error of less than 1% if the fraction of positive tests out of these 6,000 tests that we're doing is between 9% and 11%. So let's check what that probability is. The number of positive tests has to be between 539 and 660, okay? In order for this to happen. In order for us to have between 9% and 11% of positive tests among these 5,991 tests, this is the number of positive tests. So the number of positive tests is going to be between 539 and 660. Again, maybe let's pause for a moment. What are we doing here? We're checking what would happen. We go ahead and we do 5,900 tests. We want to check what is the probability that we make a mistake of more than 1%. According to the central limit theorem, it should be around 1%. Okay, this is how we have computed this number, assuming that the prevalence is 0.1. We're going to assume that we are right about the prevalence. Okay, so what is the distribution of the number of positive tests? We're doing 5,991 tests. If we want the probability that between 539 and 660 are positive, this is just a binomial, right? It's a binomial with a parameter equal to the prevalence of COVID-19, because that's the probability that each test is positive. Because remember, we're sampling at random from the population and seeing who, and carrying out these tests. So if that is binomial, we can actually compute the probability that the number of positive tests is indeed between 540 and 659 when we compute the 6,000 tests. And if you do that with the computer, okay, this looks a bit nasty, this binomial, but you just take the computer and you compute it. The probability that we're within 540 and 659 positive tests, if the prevalence is actually 1%, which is what we were assuming to compute this number, the probability is actually 99.025%. So the central limit theorem gives you an extremely good approximation of the number of people that you need. Of course, this extremely good approximation relied on knowing the actual prevalence. If we didn't have the prevalence and we had to do this approximation, then we had to do 60,000 tests, which is still much better than if we applied Chebyshev's inequality to compute the number of tests that we need. In that case, we needed 1 million, which just makes no sense. Okay, so this shows you the power of the central limit theorem approximation. Here, I'm showing you the distribution of 10,000 standardized sample means for the problem of estimating COVID-19. In this case, the prevalence is 0.05. For n equals 100, this looks kind of Gaussian, but not quite. Realize that here we're adding zeros and ones, right? And it's only a 100 of them. So of course, the possible values when you're only adding up 100 still are somewhat discrete. As we're adding over more and more values, it becomes more and more Gaussian until it converges to a Gaussian distribution as expected from the central limit theorem. Okay, so what have we learned? We have learned that the distribution of the sample mean of IID random variables with finite mean and variance tends to be Gaussian. Thank you very much.